welcome back. Saturation vapor pressure and vapor pressure are ways of, well, vapor pressure is a way of describing how much water vapor is in the air. Saturation vapor pressure is a way of describing the amount of water vapor the air could hold. But wait a minute. You know, you're at ATS 113. You've probably at least, occasionally watched weather on the Weather Channel or on TV or whatever, and what you know is they never talk about vapor pressure, right? That's not the way they talk about moisture in the atmosphere on television or on the Weather Channel or whatever. It's important in atmospheric sciences, but you know as well as I do, that's not the way we talk about it when we're talking to the public or whatever. Rather, we talk in terms of the relative humidity. You've heard the term relative humidity in your day-to-day life. They talk about they mention the relative humidity when they mention it on the radio or whatever. Let me tell you that the key definition to understand about relative humidity is that it is a measure of how close the air is to being saturated. In fact, I'm going to keep hitting that. You're going to see, I'm going to kind of annoy you. I'll keep mentioning that that's what relative humidity is. Relative humidity, the adjective relative has to be on the front here. Relative humidity is a measure of how close the air is to saturation. And in fact, it has a pretty straightforward definition. Relative humidity, which we'll abbreviate RH, is just VP divided by SVP times 100%, if that makes you happier. Okay? By the way, it does also happen to be the condensation rate divided by the evaporation rate, but we'll actually hit on that a little bit later in the module of the course. In other words, if the vapor pressure is equal to the saturation vapor pressure, which we said earlier was that that means that the air is saturated, that means the relative humidity is 100%. And if there's no water vapor in the air, so the vapor pressure is equal to 0, 0 divided by some number is going to be 0, so the relative humidity is going to be 0. See how the relative humidity goes from 0 to 100%. 0 means we're as far from saturation as we can get. 100% means we are saturated. Pretty cool. That's the key thing to say. Again, I put another thing on there, even though I already said it once in the slide. Important thing to realize. Relative humidity is a measure of how close the air is to being saturated. All right. So, if we have this definition of relative humidity as being like vapor pressure divided by saturation vapor pressure, what I want you to notice is that, look at the math here. That means the relative humidity depends on two things. In the numerator, the top of the fraction, it depends on vapor pressure, which is all about how much water vapor there is in the air. And in the denominator, the bottom of the fraction, it's saturation vapor pressure, which is how much water vapor the air could be holding. But how much water vapor the air could be holding depends on temperature. That's what Clausius-Clapeyron equation tells us. So, relative humidity depends on two things. How much water vapor is in the air and the temperature of the air. That is a weird thing about relative humidity, and it kind of makes meteorologists uncomfortable. I mean, why would the way we like to describe moisture depend on temperature of the air? Well, it turns out to be perfectly reasonable. Let's work through and see how this works. I'm going to make you two scenarios. One's going to be in the summer and one's going to be in the winter. I just picked summer and winter because I wanted to show you something where it was cold and someplace where it's warm. Alright, so here's my happy little winter house here. And what I want to do is I want to take some air from the outside of the house, determine its relative humidity, and then I'm going to bring the air into the house. In this case, I'm going to heat it up with a furnace and then see how the relative humidity changes. Alright, so let's take some sample of air from the outside of the house. We're going to use whatever kind of instrument it is to measure moisture and stuff like that. We'll get there in a little bit. And figure out what the relative humidity is. Alright, let's take some air outside the house. We're going to measure the temperature of the air. And let's say the temperature is 0 degrees Celsius. Now, we could use the graph of the Clausius-Clapeyron equation and read off of that graph what the saturation vapor pressure is. That's what the graph of the Clausius-Clapeyron equation is for. And let's say we get 6 millibars. I don't remember if I actually guessed that number or if I actually looked at the graph when I made the slide, but whatever. It's in the ballpark. When you have a temperature of about 0 degrees Celsius, a vapor pressure of about 6 millibars is probably all the more water vapor the air can hold. Alright, then let's say we actually measured the amount of water vapor in the air outside the house, and let's say it comes to 5 millibars. Again, we don't actually have an instrument that measures vapor pressure directly. We have other instruments that we can do math and then figure the vapor pressure out, but good enough. So we have a vapor pressure of 5 millibars, a saturation vapor of 6 millibars. Since relative humidity is VP divided by SVP, 5 divided by 6 works out to 83%. Therefore, the relative humidity outside of this house is 83%. We are 83% of the way to being saturated. Okay. You open the door, cold air from the outside comes in. Do you leave that air at a temperature of 0 degrees Celsius? No, of course not. You have a device in your house that heats that air up in the winter. We call it a furnace. So if we put that air into the house on a cold winter day, we have to heat the air up. How does that change the relative humidity? Well, all right. We're going to measure the air now. We see that it has a temperature of, let's say, 20 degrees Celsius. 20 degrees Celsius works out to 68 degrees Fahrenheit. We could read that off of the Clausius-Clapeyron equation, and we could, or off the graph or whatever, and we could find out that the saturation vapor pressure for the air, now that it has been heated up inside of the house, works out to something like 24 millibars. Okay? 24 millibars. But what's the vapor pressure of the air? That's a measure of how much water vapor is actually in the air. Well, we didn't do anything yet to actually add any water vapor to the air, so it still has 5 millibars of water vapor, of vapor pressure in there. So the relative humidity, which is vapor pressure divided by saturation vapor pressure, will be 5 millibars divided by 24 millibars, which works out to 21%. The relative humidity of that air when you brought it into the house is now 21%. Outside it was 83%, inside it becomes 21%. Oh man, we changed the vapor pressure of the air, the relative humidity of the air just by changing its temperature. By warming the air up, we got it farther from being saturated. It previously was at 83% relative humidity, now it's at 21% relative humidity. In practice, 21% relative humidity is pretty darn low relative humidity. That's not comfortable. You're going to get carpet shocks, your lips are going to be chapped, your skin's going to be itchy. We don't usually like to live under those conditions, which is why most houses have some kind of humidifier that adds water vapor to the air in the winter so that the vapor pressure starts going up, so that when you compute the relative humidity, you get a bigger number than like 21%. Often the humidifier is an appliance that is in your living room or something like that, and every few days you add water vapor to it. In most modern homes, it's actually part of the furnace itself, and you don't know anything about it. I mean, it just adds water vapor as it's warming up the air and whatever. Your parents take care of it. All right, because you don't want to have relative humidity that low. Let me show you another example here. Let's talk about a situation in the summer. Okay, we're talking now. I'm just going to get that way. I have a warm air that I'm going to cool when I bring it into the house. Okay, so let's take a sample of air from the outside of the house. Let's say that it is 30 degrees Celsius outside. 30 degrees Celsius is, I think, 86 degrees Fahrenheit. And we could actually use the graph of the Clausius-Clapeyron equation, or God forbid the equation itself, and find its saturation vapor pressure. And let's say it's 44 millibars. Okay. In other words, if the air were saturated outside, it would have 44 millibars of vapor pressure. But we use whatever piece of equipment it is that we have that we can measure humidity with, and we can do the necessary math, and we measure that the vapor pressure outside right now, the actual amount of water vapor in the air, works out to 23 millibars. Okay? So if we do the math where we saw that the relative humidity was the vapor pressure divided by the saturation vapor pressure, we'll have 23 divided by 44, you get 52%. The air is holding 52% of the water vapor it would be holding if it were saturated. Okay, fine. Then we're going to open up the door in the house, bring some hot air from the outside into the house. Clearly, we're not going to leave the air in the house at 86 degrees Fahrenheit, 30 degrees Celsius. We're going to cool it using our air conditioner. So we bring the air in, we bring it in, cool it by the air conditioner. What's going to happen here? All right, we'll cool it to 20 degrees Celsius. That's 68 degrees Fahrenheit. That seems like a pretty cool day in the summer in your house. Let's cool it to 20 degrees Celsius. Well, if we cool the air to 20 degrees Celsius to make it more comfortable in the house, the saturation vapor pressure will now be 24 millibars by plugging it into the Clausius-Clapeyron equation or looking on the graph of the Clausius-Clapeyron equation. But we haven't done anything to change the amount of water vapor that's in the air. Okay? We still have the same amount of water vapor molecules in that sample of air when it was outside as inside, so the vapor pressure is still 23 millibars. Since relative humidity is vapor pressure divided by saturation vapor pressure, it's 23 millibars divided by 24 millibars, which works out to 96%. The air is now holding 96% as much water vapor as it would be holding if it were saturated. Notice what happened to the relative humidity. It went up when we cooled the air. It went from 52% relative humidity outside, same exact sample of air became 96% relative humidity when it came on the inside. Is 96% of the way to being saturated. We made the air We increase the relative humidity by decreasing the temperature of the air. We brought it closer to being saturated by chilling the air. Now, in practice, 96% relative humidity would be very uncomfortable in your house. You would be sweaty, it'd stick to the furniture, your basement would get moldy, it would be very uncomfortable. So in practice, most homes have a dehumidifier that removes water vapor from the air in the summer when the air conditioner is running. Therefore, the numerator, the vapor pressure, the amount of water vapor molecules in the air decreases and the humidity doesn't get that high. Okay? You might actually have a dehumidifier as an appliance that sits in your house and it extracts water vapor from the air by condensation and collects it in a bucket that you dump once a day. Plenty of homes have that. But actually in most modern construction and so on, the dehumidifier is just part of the air conditioner, part of the air handling system. It constantly is removing water vapor in the summer so that the relative humidity inside your house doesn't get so high. But let's be clear about this, because changing the relative humidity is going to be an important part of the rest of this module, because it's going to be about making air saturated. How are we going to make clouds? How are we going to make fog and so on? Well, looks like to change the relative humidity, the left-hand side of this equation, we're going to either need to change the numerator or the denominator of this fraction. The numerator, the top part, well, we could add or remove water vapor as a way of changing the relative humidity. That can be done. In practice, that's kind of the hard way to do it, though. Most of the time when we're going to change the relative humidity of air, we're going to do it by changing the denominator of this fraction at the bottom of it. We're going to change the saturation vapor pressure by changing its temperature. We're either going to warm the air parcel, which brings it farther from saturation, or we're going to cool the air parcel, which brings it closer to saturation. In practice, this is going to be the story about how we're going to be having condensation happen and saturation happen in the atmosphere. This is going to be, we're going to cool the air to its saturation vapor pressure. Well, we're going to cool the air, and it's going to get closer and closer to saturation. In fact, if we cool it enough, we'll actually get the air to be saturated. Remember, as we cooled the air, the relative humidity went up. We brought it closer to saturation. Well, if you bring the relative humidity up enough, you'll get it to 100%. You'll get it to this temperature at which the air is saturated. That's an important temperature. That's the dew point. TD is our abbreviation for dew point. Temperature D, dew point. It is the temperature to which you would need to cool a given air parcel for it to become saturated. This air parcel I'm holding right here in my hand is not saturated. It has some relative humidity that's less than 100%. If I started cooling it, its relative humidity would go up, because the saturation vapor pressure, the amount of water vapor it would be holding if it were saturated, is going down. At some point, if I cooled this enough, it would have a relative humidity of 100%. It would be saturated. That temperature to which I had to cool that air parcel for it to become saturated is called the dew point temperature, which is totally weird if you think about it. It is a temperature. But it isn't the temperature of anything. It's not the temperature of the air. It's not the temperature of the water molecules or anything like that. It's the temperature, it's kind of a hypothetical thing. It is the temperature to which you would need to cool the air for it to become saturated. For the amount of water vapor that is currently in the air to be all the water vapor the air could hold. If the air is very humid, I don't have to cool the air all that much, and that large amount of water vapor that's in there will be all the air parcel can hold. So my dew point won't really be all that low. If my air is very dry, I might have to cool the air parcel a whole lot before its temperature, before that little bit of water vapor that it has in it is all it can hold. In other words, dew point is a measure of how much water vapor is in the air. When the dew point is relatively high, the air is humid. When the dew point is low, the air is very dry. Notice the dew point has to be less than the air temperature, because it is the temperature to which you cool air for it to become saturated. In fact, the only situation where the dew point and the temperature are equal is if the air already is saturated. So dew point turns out to be a way to describe the amount of water vapor that's in the air. And this idea of cooling air to its dew point so that it becomes saturated and is no longer able to hold any more water vapor is going to be the fundamental way in which we're going to get clouds and rain and fog and dew and so on. We're going to talk about that more in that bringing air to saturation lecture that's going to come up later in this module, rather than trying to squeeze like 60 more slides right here. But this idea that we cool the air to its dew point temperature for it to become saturated and then start doing something like making cloud, making rain, making fog, making dew, whatever, is going to be our primary way that we're going to make that happen. How do you calculate or determine the dew point of air, like mathematically? Turns out you can use that graph of the Clausius-Clapeyron equation. We just use it the other way around. Previously, with those red arrows there, we used the temperature of the air. We followed it up to the curve there, and then read across to the y-axis to find the saturation vapor pressure. But we can use the graph the other way around. If instead of saturation vapor pressure, if you sort of covered up the word saturation, you just knew the vapor pressure of your air, let's say like on these green arrows here, the vapor pressure was 25 millibars. We measured that or computed it somehow. You could read across to your curve and then down, and where you read on there would be not the temperature of the air, it would be the dew point of the air. You actually have to do that in one of the homework problems. Okay? You can use this graph to compute the dew point of air if you know the air's vapor pressure. If you know how much water vapor is in the air, you can figure out the temperature to which you'd have to cool that air for it to become saturated, which is totally cool. All right, we have one more part to this lecture here, but before we get there, let's answer 3 quick questions. Question 4. Increasing the temperature of an air parcel without changing the amount of water vapor in it, blank the relative humidity. If we change the temperature of an air parcel, does that increase the relative humidity, decrease the relative humidity, or does not change the relative humidity? Make a choice from those 3 options and get a little feedback before we move on to question 5.